Welcome to the shop. Today we have the question. Okay, you probably saw from the title. That's why you clicked on this video, because you want to find out too. If you open your drawer and you have a motor on it, in it, and it doesn't have like any real specifications, or it's an old one and the Wayback Machine isn't giving you any love. So you've got this motor and you want to figure out what the specifications are. There's a certain way to do that because math exists. And I'm going to walk that through you. Now, I got to say, I have friends that are enablers. And so as I was thinking through like the GBZ, the 33% GBZ, I was like, oh, okay, I've got an electric motor that'll work for this. And then my buddy Ben said, hear me out. So this is the tiny little motor that I pulled out of my drawer just for demonstration purposes. I don't know what the KV is, but I can use this number approximating that this is probably a Supo motor, and then, do my Google box machine search and figure something out. But this is the motor that I was thinking of using for the GBZ. This is a Sunny Sky 190 kV 40cc motor. I mean, it says performance motor 7025 kV 190. I can Google box that. I can figure out everything that I need to figure out like what size prop I need. But then Ben sends me this package in the mail. So we have Whittle Bitty Baby Moto that handles like maybe 300 watts to big motor that handles like 6,000 watts to holy mother of mercy, what is this? So this is a big motor that Ben acquired, and we wanted to see if it would work for the GB project, but we didn't know any specific numbers about it, or we had doubts. And so I'm going to take you on a journey today to figure out all the statistics about this motor. We're going to bleep bloop it into computer boxes, spit out some numbers, because science is a real thing. I'm a scientist by profession. This is what I do, what I get paid to do. I don't get paid, well, ish, to do YouTube stuff. So I'm going to show you my methodology and how to do this. And, some of this is going to be back of the napkin. Some of it's going to be approximation, but that's okay. I'm going to walk you through it anyway, because this is certainly something that I've come across before. And I was like, do I really want to go through with it? This? Yeah, I absolutely do. Yeah. It's a good thing. Okay, so I'm going to turn you around and explain the first parameters. Well, I'm going to show you the equipment that we need. So on your bench, you really should have a couple of multimeters. And I say a couple because at one point you will need two. These you can purchase for like $5-10 off of Amazon. Not a huge deal. This one I actually got for free. Someone was giving this out at the flying field, and I was like, ooh, I could use one to throw in my Go box. And now I have two. So then I have this old one, which is a little bit better for measuring amps. It's a bit more suited for high current applications. And in addition to that, you're going to need some alligator clips. So snag up some of those off of Amazon as well. And just a run-of-the-mill ESC. Doesn't have to be anything too terribly big. I'm using a 40 amp garbage ESC. I mean, Hobbywing makes some good stuff, but this is not what I'm going to fly with that or that. But yeah, I might throw that on that. Anyway, so we've got a three cell LiPo, just basic 2200 pack. We need a watt meter, and we've got a little receiver, and this is a 10 watt, 10 ohm power resistor. Again, pick this up off the Jungle website. You're also going to need a drill. I opted to use a corded drill because a corded drill is going to give a more reliable RPM. Okay, we need to measure some RPMs, and you want to make sure that from one measurement to another, because we have a couple of phases we have to deal with, right? So you want to make sure that, like, if you've got a battery powered drill, make sure that it is fully charged and that your voltage sag is going to be minimal. Because, I mean, honestly, like, spinning this motor, it's hard to convey on camera, but it's difficult to turn this. And so you're going to have resistance in some form or another, and you want to make sure that this is constant because you're going to spin this motor to take a measurement 3 times. That's a lot of talking, a lot of explaining, so let's get down to the science and do our first measurement. All right, so the first thing we have to do is establish what the RPM is of the motor that we're gonna be working with. Okay, so that has to be part of the mathematical calculation. The way that we do this is we have to measure the frequency. Now, as this is essentially a phased DC motor, when you spin this, you are generating an alternating current from this. And we can determine that frequency by measurement. Okay, so I have a multimeter that measures frequency. So I've got it on the Hertz setting, and this will tell me what the frequency is. And so I hold it on each one of 2 leads, doesn't matter which 2. And then we're going to connect this motor, and I did have to 3D print this. We're going to connect this drill to the motor. And then we're going to hold 2 leads and observe what the frequency is. All right, so that said 0.765 kilohertz. If you're watching and following along for real, you'll know that that is, move decimal point. Kilo means 1,000. So move the decimal point. So yeah, 765 hertz. Okay. All right, so the next thing that we have to do is we have to figure out the number of poles that this motor has. And the number of poles is not the number of poles on the stator. It's basically you're looking for the number of magnets, okay? So usually there's some sort of weight to balance the assembly, so you can start there. Or you can take a Sharpie and mark it on the bell and then just count all of the magnets. All right, so we have 42 poles on this motor. All right, so the next thing we're going to do is we are going to switch our meter over to our voltage, and we're going to select AC. So we're going to try to get the volts here in alternating current. Now, the way we're going to do this is we have to measure this essentially 3 times, okay? There are 3 combinations, okay? So we've got one combination here where you've got this pole, and then we're going to move to that pole, and then we're going to move to that pole. There's no real positive or negative just because it's alternating current. We just need to get a measurement on each of the 3 poles. And what's worth noting here is this does generate voltage. And I think you might be surprised at just how much voltage this can generate. So again, we're going to rotate at maximum RPM for the drill so that we know that it's constant and consistent. So we're going to make some noise and try to be safe here, not shock ourselves, not send the motor flying or anything like that. So we'll do slow spin up. We'll try to get a settle voltage. Okay, that was 86.8 volts. Next pole. Eighty 87.2. And I just broke it off of the 3D print. All right, so now we are sitting down at our computer and it's time to do math. So I believe in letting machines do math because I'm human and I make mistakes. So we make sure that the formulas are right. So let me walk you through the formulas. So we're calling this motor Big Mama. We have the drill frequency, 765 hertz, and the motor poles is 42. And when we look at the formula for this, it's a constant 120 times the C2, which is our drill spin frequency, and that divided by the number of poles. And that gives us 2186. That's our motor frequency. So then when we measure our voltage, we have measurement of the voltage at pole 1, which was our 86.8, pole 2, 87.2. And since we broke off the adapter, I just used the point in the middle and gave us an average of 87 volts. 87 volts AC. Now, just keep in mind that what comes out of your wall is at 120. That's 40 volts off. That's not going to feel comfortable. We'll just say that. So, yeah, exercise some caution here, folks. All right, so after this, we're at the stage where we're ready to calculate our kV. And our kV is RPM per volt, right? So we have C4, which is our RPM, divided by our volts times a constant, okay? So our motor is in fact measured at 19 kV. I don't know about you, but 19 is low. That is a low number. Now, at this point, we can start, doing back of the napkin kind of math and say, well, wait a second. The amount of volts that we get here, we have, let's do 4.2 volts on a fully charged battery cell. And the most number of cells that I can find an RC application speed controller for is 14. Times 14, that's 58.8 volts. Okay, so now we can take that 58.8 volts and multiply it by our kV. So without even getting a propeller on this and loading it down, we're only at 1100 RPM. Okay. So for reference, the full scale GBZ was like 2400 RPM. Okay. So we're never going to get there. We're never going to get there with this motor. Keep in mind that the scale prop size is like 33 inches. Now we could go down to like a 32. Zor makes 32-inch props, but they only go up to like a 16 or 18-inch prop pitch. And that still only gets me to like 20 miles an hour. Okay, so at this point, the exercise is over in terms of application of this Big Mama motor to the GBZ. But let's keep going in our analysis of the motor just as an exercise so that we can learn something. So the next set of values that we need to get is I/O. Okay, so IO is a measurement where how much current does it take to spin the motor with no load, and usually across the industry it's standardized as 10 volts, and so that's why we're going to just use a 3-cell battery, because we can measure the voltage using our standard meter. So our meter here, just basic watt meter, when you plug it in, it's going to show me my volts and the current when I start to run the motor. Now, this doesn't have to be anything too terribly amazing, mostly because, yeah, this isn't going to spin very fast. So we're going to actually wire this motor up to this speed controller, plug it in, and I've got my radio programmed to use this basic receiver on the bench. We're going to spin it up and look at our watt meter to get the current that it's drawing at maximum RPM and the volts that it is reading as well, and we'll plug that into the spreadsheet. Okie dokie. So we have our assembly here. We've got our battery plugged in, connected to our radio. And yes, I am using masking tape to hold these connections together. So all I'm going to be doing is running the throttle up and looking at my meter here. And you guys will be able to see exactly how stupid slow this is on a 3-cell pack. All right, so we're at 0.2 amps at 11.89 volts. Okay, now stay with me here. Stay with me. This is going to look like a hot plate of spaghetti, but I'm going to help you follow it. It's pretty straightforward. We have to take 2 measurements at the same time. That's why we need 2 multimeters. But the wiring can... Let me just walk you through it. Yeah, it looks kind of crazy, but really quite straightforward. I'm going to walk you through. We're going to start at the battery, okay? We've got a positive and a negative, okay? So we are using alligator clips respectively. So this alligator clip is going to our first multimeter, which is going to measure current, okay? We're going to measure amps, okay? And then the output will then be the positive, okay? And then that goes to 1 wire on the motor. That's going to go through 1 pole and going to come out another. And then that is going to complete the circuit with our power resistor, our 10 watt, 10 ohm power resistor to our battery. Now we need the resistor, otherwise we go splody on our current, okay? This directly applied to that makes magic smoke, okay? This will prevent magic smoke from happening. Very, very important. And touching this is our on-off switch. You'll note that there is another here. We have to measure voltage. And so that is why I have an alligator clip that goes to nothing, just holding these onto the wire, and then this alligator clip holds on that to the wire. It kind of doesn't matter if you get a negative number on your DC voltage here. It doesn't matter. You can take the inverse of that. The absolute value is what we're after. So with that, we are going to do this 3 times. You can do it for each of the poles and then get an average. But there is more math involved, so let's get our measurements. All right, so these are all going to be more or less the same on each of the poles. So I'm only going to do it once. And you want to make sure that you're doing this for no more than 4 or 5 seconds. You want it to become stable on your readings, but again, we're trying to prevent the motor coil from burning out. So this is my on switch. Volts at 158.8, 0.113 amps. back at our spreadsheet, we've got our 0.1588 volts or 158.8 millivolts, and our amps, which is 0.113. Now, the coil temperature, this is an interesting one. If you have an IR gun, like an infrared thermometer gun, you can measure the coil temperature and see if there's an offset. If not, this is in centigrade Celsius. Make sure that you're entering just a 20 if you don't know. And then the equation looks like that. You've got a constant, and then you've got your average room temperature, which is 20 degrees, minus this to get an offset. So essentially, we make this 1 in the equation. And then you've got your C12, which is your volts, and then C13, which is your amps. And so this is your formula that all calculates out to be 1.41. So now we're in eCalc. I prefer eCalc, this online motor calculator. So we're just going to go with 5,000 and let's say our 14S battery controller, 300 amps, why not? Our motor, we're going to leave that be because we're going to enter our custom information. So our KV we know is 19. And this is our IO, our no load current. So that is 0.2 amps at 11.89 volts. So 0.2 amps at 11.89 volts. We don't know the watts, so we'll just say 6,000 on a whim. And then our resistance. Our resistance is our RM that we calculated at 1.41. 1.41. And then we can put a prop on this. Let's just do a Zor Sport prop, and we'll do our 32-inch prop at 16. No, let's go with 18-inch. And calculate. All right, so I've gone back through and just picked another motor so that I would auto-populate this case length. Our number of poles we know is 42. But yeah, the weight and such, that kind of just doesn't matter. Anyway, so calculating this all out. So yeah, even putting a 32-inch prop, 3218 on 14S, we're only going to be pulling 79 watts, which is ridiculous. Estimated speed, 19 miles an hour. 19 miles an hour right there. That's ridiculous. So that would never fly. Our RPM, estimated RPM with the loaded prop is 908. So that tracks pretty well. Yeah, it's just a absolute not match for the GBZ. So as you can tell, this has been an absolute blast for me to sit down and actually measure some stuff. I highly recommend that you invest or at least go through the process of this at least once. It's not hard, but it just takes a little forethought and careful planning and honestly being a little safety conscious. It's been a fun exercise to go through this and report back to Ben to say, hey, thanks, but no thanks. And I'll send this back so you can put it in a electric go-kart or something. Maybe if you were to gear this or like do a belt drive system, like 4-to-1, you could make it fly, possibly. Anyway, it's all about learning new stuff. And like I said, if you get into your drawer and you just don't know what's in your drawer, now you can find out. How much power is it going to be able to handle? Don't know. But that's what, reasonable measurements after that, you can get a rough starting place is really my best suggestion. Start with a prop, go with another prop, get some power readings, and do your bench testing, do your homework, and have fun with that. Until next time, I am going to keep going on all the projects that I love here in my shop. Make sure that you're getting the supplies that you need at Dubro to build those projects of your own. And until next time, keep working on and learning about your flying works of art.